Right, we've got all the pieces in place now. We've got our point distribution models built on principal component analysis, and we've got our way of organizing our data so it's in a standard position. And now we're in a position to be able to learn the models of the shapes that we're interested in, our T-shapes, and then also recognizing those shapes. So what we're going to do in this little segment right here is look at the theory of putting all of those together and a little bit of the implementation as well. So let's talk a bit abstractly now, just to start with. We've got a set of shapes, and what we want to do is we've got our structural model, we've got a new unknown sample X, we've got a structural model, and we've got our statistical model. And what we want to do is we want to be able to estimate whether or not this new sample is one of those objects that we're trying to recognize. So the way that we do this is that we project our unknown sample onto all of our onto our axes, as we got before, and now we get our new weights. I guess we have to subtract the mean first to get the weights, just as we do for normal principal component analysis. And that gives us a new weight-based description of our unknown sample in our new point distribution model space. And then for each of the classes that we have represented previously, we can now look at how close is this new re-represented shape to each of those classes. And what we're going to use for that is what's called the Mahalanobis distance. We'll talk a little bit more about that in a minute, about why we use the Mahalanobis distance, but the Mahalanobis distance is given by this formula right here. So for each of those classes, we can look at the distance of our new shape to the model of that class, and then we can pick the class which has the smallest distance. And that's how we can say the object, this new object X, is an instance of one of those classes. We can also reject the decision if the smallest distance is too large. So this is great right here. This allows us to look for different structural variations in each of the different objects by looking at the different classes. And we've also got our statistical model of the class with the mean and covariance matrix, which says what's the range of normal shapes that one might expect for that class. So we can look at both the structural component and also the statistical component and recognize or reject that shape. Well, in order to apply that approach, we need to have some sort of a model. And this summarizes how we actually might build that model, particularly for our T-shapes. So as before, we always start with our binary image. We've got to load the image, we need to find the boundary and the corners and all that sort of thing, except for now we've got better corners. In order to build our point distribution model, we need to have our T-shapes in some sort of a standard position, so we're going to rotate those shapes. Once we've got it in the standard position, we can get the vertices of that shape and make ourselves a vector, and we can concatenate the row and column coordinates to make the long vector that we looked at for building the point distribution models. We can build our structural model using principal component analysis, and then we can project all of our examples into that new principal component weight space. And finally, once we have those weights in that lower dimensional space, we can build our statistical model that we can use for our Mahalanobis distance. So that's the essence of building the model right here. Once we have the model, we can then go through the process of recognizing the objects. Okay, in much the same way, we do the basic image processing, and we then look for the boundaries. We got a little bit of rejection if we don't get the 8 boundaries, because we need to work in exactly a 16-dimensional space. If it has more than 8 vertices, we're not going to be able to do anything with it. There's some tricks that we could use to kind of clean up the data, but we're not going to go into that here. Right, so we've got 8 vertices. We build our, we rotate our T into its standard position using the same sort of heuristic algorithm that we looked at in the model learning stage. We extract all the vertices. We build the long vector that we've talked about. We project that vector in the principal component space, and then we evaluate the likelihood of that projection again using our model and the Mahalanobis distance there. So that's the kind of the core of that. Now we're going to look a little bit at the some of the MATLAB code which implements some of that. As I said previously, you can find all this MATLAB code on the lecture web pages as a resource that you can look at, you can use, you can download, you can try yourself. In this case, we're going to have 31 sample images. We're going to want to load each of those images. We're going to sort of prompt the user with a prompt statement asking for a string, which is the image stem. That's sort of where to find the files and what their the file family name is. And once we've got that, then we want to load in the images one by one. So we're going to iterate over the 31 images that we've loaded in. Here's another little bit more MATLAB kind of tricks right here that you may find useful. We want to read in an image. We need to construct the name of the file that holds that image. So we're going to have the stem image. We're going to take the number, the file number, the instance of 1 to 31. We're going to turn that from an integer into string. We're going to concatenate that with the file stem, and we're going to concatenate JPEG onto the end of it. So that's building the string. That's the name of the file, and then we're also going to tell this image read function, which is a MATLAB built-in function, that it's a JPEG file, and it's going to load it in. It's going to be loaded in as a color image. All these images were originally color images. When we're going to do our processing, we want to have a gray level image, so we can use this MATLAB RGB to gray function, which turns it into our gray image. We can find the binary image as we did before. We can find the parameter as we did before. We can clean up the boundary as we've done before. We can find the track around the boundary, and we can find the corners. Okay, so these are all steps that we've sort of seen already and don't need to worry about right here. Well, at this point, now we want to know how many lines that we found when we found the corners right here. We expect that there should be 8 lines because there's 8 vertices. So if it's equal to 8, we're doing fine, and we can kind of carry on. If it doesn't have 8, then we have to sort of skip this particular example right here. We want to rotate the T-shape into a standard position. We're not going to, these are the heuristics that we were looking at previously. We're not going to go into the details of them now. Anyway, so we've got a set of lines that are now in a standard position. Once we've got the lines, we want to be able to pull out all the vertices. So this little function that we built here sort of pulls out all the vertices one by one and makes them into a big long sort of list right here. And that gives us all our sets, and we want to now be able to take all these vertices and add them to a set of all the vertices. Okay, so we're going to loop one by one through all 31 of our training samples to build up our training data. So this all vertices array right here is going to have 31 samples, each of which is a 16 vector, because we have taken our 8 data points, and it has the row and column coordinates, so that makes 16 there. Right, so that's our data, and we've done that for all 31 of our test images. Once we've collected all that data, we can easily find the mean vertex, which describes that model. We can find want to find the covariance matrix or the scatter matrix, and we can easily do that by a little bit more MATLAB magic, using the ones command and the mean vector to subtract the mean vector from all the data, and then product the two of them together to give you the scatter matrix. And now we want to do our principal component analysis. This is off the raw data. We're trying to build our structural model, so we do our principal component analysis. MATLAB conveniently has a singular value decomposition function that does that for us. We take our scatter matrix, that gives us our U and D and V matrices that we need for the principal component analysis. We want the principal axes, so that's where we look at the V matrix, and in this case we're only going to use the first 5 components. We'll see a little bit about why we only use 5 later in another little lecture segment, but here we're only going to use 5. So that gives us our, let's say, our model vectors, and we want to be able to project our original data, so that was all the vertex data, down onto the new model coordinates, this 5-dimensional vectors, the 5-dimensional coordinates that we've selected right here. So we use a bit of MATLAB matrix multiply that projects it down to get our set of vectors. And so now we have 31 sample vectors, each of which is 5 of dimension 5, and we can put all of these together to build our statistical model, and that's what the next step is right here. We got our mean vector and our covariance matrix, and in this case we're always going to want to use the inverse of the covariance matrix, so we compute this once. Anyway, the build model takes all of that data and computes that for us. Finally, we're going to want to save all this data so we can use it again and again, and so we're using a MATLAB sort of save command that saves all of these sort of components of our model right here, and we can reload it for future use. Right, so that's a little bit of MATLAB code that sort of illustrates all the details of this model building process in a little bit more detail. As I say, you can find all of the actual code that was given by all these functions on the lecture website. Well, one of the things that we talked about using in the part of this recognition is using the Mahalanobis distance. I want to talk a little bit about why we're using the Mahalanobis distance. So normally if we have two different vectors and we want to see how close together they are, we use the Euclidean distance between them, sort of the vector distance. And that normally works just fine if all of the dimensions are, you might say, equally important and equally independent. But when we've built these point distribution models, sometimes some of these vectors have some sort of correlation between them. Also, there may be a difference in the range of values. Some of the coordinates of the vectors may have quite a large range, and some of the others might have quite a small range. And between these two effects, the correlation and the scaling, this can create problems when trying to compute the Euclidean distance. So instead of using the Euclidean distance, we use what's called the Mahalanobis distance. And this looks very much like the Euclidean distance when you rewrite the Euclidean distance in slightly more expanded vector form. So normally we sort of see it abbreviated as this, but really it's the difference of the two vectors, we dot product them together, and we take the square root. Well, the Mahalanobis distance is essentially the same, except for embedded in the middle of that we've got our covariance matrix right here, which does that's the scaling that we want to be able to decorrelate the different values that are in the individual vector components and also scale them so that they're in a similar range of values, which improves the numerical capabilities of the operation. So anyway, it's a big long name, sounds like a complicated idea. In practice, it's really quite simple. You just embed the covariance matrix in the middle of your distance calculation. Well, once we have all of the model built together, we can do our recognition quite easily. If you remember back to when we were talking about the sort of the theory and the outline of the recognition, you saw it was very similar to the training kind of case. And indeed the code is virtually identical. It's just down to the final stages that we really need to do a little bit of something which is different. And that's sort of summarized right here. So if we have our new sample and we've rotated it into the correct position, we've detected it in the binary images and all that kind of thing, we now have our vertices that go around the shape, and we've oriented it into place. We can turn it into our 16 vector in the same way as we did with our training data. And we can use the MATLAB reshape command to do all of that. And we now have our model, which has the mean vertex of the model and the deviations from each of the different principal components. Okay, in this case we were dealing with 5 for our T-shapes. So we introduce that into here. So this projects it into the new weight space. So this is our sort of weight-based description of our original shape, our unknown shape, and our five-dimensional shape. And now we can look at our Mahalanobis distance and see how close is this new shape to the family of shapes that we expect to see. The mean given by the mean vector and the covariance matrix that describes the distribution. So that gives us our Mahalanobis distance. And if that distance is small, we can say, yep, we've recognized this shape. We've got a good instance of something from our training class right here. We'll see examples of that coming up in just a minute. So what have we learned here? Well, we've looked at a way of using our point distribution model and our statistical classifier and our Mahalanobis distance to build ourselves a way of recognizing a set of shapes that may vary, may deform over a whole family of shapes. And we did this by extracting the structural variations and then looked at the statistical variation which is allowed for those shapes. Thank you.